Yeah, good morning to one all present over here. Um, First, I would like to thank St. Joseph team members for inviting me to give a guest lecture the topic of data analytics in power quality. Uh, from the team members, they have introduced me. Myself, Dr. M.K. Ilangu, Professor and Head Department of Electrical and Electronics Engineering, K.S. Rangasamy College of Technology. Yeah. In my today's presentation, I would like to give the following in detailed manner. Introduction to power quality, right? What is the power quality? How the power quality issues are going to happen in the power system network, like even transmission, distribution, utilization parts and all. And what are the benefits to the society, right? Why do we need to study the power quality issues and why we have to start out the power quality issues related with that, what are the benefits to the society with the help of power quality, I would like to explain to you. And where are the applications of power quality, right? Where are the places power quality needed, and what are the existing methods to determine the power quality, right? See, and the existing methods, what are the drawbacks, and what are the proposed methods, right? Actually, in my past research, I have done the power quality analysis with the following proposed methods, like Hilbert-Huang transformation, backpropagation algorithm, radial basis function, and locally weighted projection regression methods, right? See, in these cases, how the data part is going to be helpful, right? Without having the database, we are not going to do anything, right? So in this power quality, how the database management system is going to be useful for that, where we have to use the particular data and how it is going to be analyzed, and how these data are going to use with the help of uh, artificial neural networks and all. I would like to explain to you. Then finally, I would like to compare the proposed algorithms like Hilbert-Huang transformation, backpropagation, radial basis function, and locally weighted projection regression methods. And finally, I would like to give the conclusion. Right? See, these are all the things I would like to share with you in today's guest lecture. Yeah. Introduction to power quality, right? See, we know that it's a basic definition, basic explanations of power quality. Any power problem manifested in voltage, current, or frequency deviation that results in failure or misoperation of a customer equipment, right? See, normally we know that in all domestic appliances or in commercial appliances, they are in need of some constant voltage, right? See, for example, if 230 volt 230 volt is the rated voltage of a single phase supply, right? See, for this rated voltage, all the electrical devices like even like our domestic appliances like refrigerator, washing machine, grinder, everything uh, are going to be performed in efficient manner, right? See, if there is any voltage deviation, instead of getting 230 volt, sometimes it may be less than uh, it may be less than 230 volt, like 220 volt, or sometimes it may get 180, 190 voltages and all, right? So if there is any voltage deviations with respect to rated voltages, right, it may be less than rated voltages, or it may be greater than rated voltages, right? See, in sometimes we, instead of obtaining 230 volt, we have to obtain 240 voltages and all, right? See, whatever may be the situation, if it is 230 volt, or sorry, less than 230 volt, or greater than 230 volt, it is the power quality problem, right? See, not only with that of voltages, it's also with the frequency, right? We know that in Indian standard systems we are using 50 hertz power frequency is the cases, right? So instead of 50 hertz, there is 50 completed cycles per second. If you had to obtain 48 hertz or 49 hertz, or it may be sometimes more than 50 hertz, like 50.15, 51 hertz and all, again there will be a power quality problem, right? So if there is any deviations in voltages, or if there is any deviations in frequency, or sometimes there is any deviation in current, right? See, normally current is not going to be, is not going to, the current derived from the power supply is purely depends on how much amount of electrical load which is connected, right? See, for example, if 2 kilowatts load is going to be connected to that sources means according to that 2 kilowatts, right? See, what is the power factor and what about the rated voltages? That required current has to be taken from the sources, right? See, that required current which is flowing through the load has to be a pure sinusoidal waveform instead of pure sinusoidal. If there is any deviations in the current, what is this? Again, the net resultant current is not going to be the required values, right? It's not equivalent to the required values, right? So again, what is this? Again, the harmonics problem. Again, the problems are going to be uh, occurred. So what is the power quality? The power quality generally it will be explained in the following manner. Any power problem manifested in voltages, right? Voltages, current, or frequency deviations that results in failure or misoperation of customer equipment, right? See, customer equipment means all domestical appliances or in maybe in transmission systems, all power system devices like insulator, conductor, everything are going to be taken into account, right? See, these are all not going to be function in a proper manner, right? And when we look at what are the causes for the power quality, the main causes is the aging of electrical equipment, right? See, for example, like automobile, that electrical devices also have certain age of the components, right? See, for example, if the particular motor is going to be run, if the particular motor is going to be run means there are some of the ages, right? See, for a period of some 2 months or 3 months, the brushes are going to be replaced, right? Normally, the brushes are not going to be used for longer period. Similarly, the conductor, bushings, everything are going to be replaced for a particular working operation time period, right? So, if you are not going to replace it properly, unnecessarily heat is going to be produced in the electrical motor, right? See, electrical motor means instead of the electrical motor, we have so many parts, right? So for each and every part, we have to be replaced. It depends on the usages, right? See, if you are not going to replace it, again, what is this? Our quality problems are going to be existent, right? Then improper maintenance, right? Improper maintenance is same. Just like replacement, we are going to do the maintenance work. See, for example, if transformer means the transformer oil has to be checked, that the transmission line insulator means we have to check what is the operation of this insulator, what is the property of the insulator, whether it is going to withstand. Everything are going to be measured, and we have to do the maintenance, right? See, while doing the measurements, if I had to find out the particular equipment is not going to be function, it is not, it is loses their original property, we have to replace it, right? Unless otherwise, there will be a power quality problems, right? See, just the thing that it has to consume over amount of electrical energy, so causes that heat is going to be produced. Once heat is produced, it leads to energy losses. Again, the power quality problems existed in the cases, right? Then fluctuations in the power consumptions. We are not going to predict accurately, very accurately, what is the power consumptions of our electrical load, right? See, even in our home, we are not going to predict at what time we have to switch on the fans, switch on the TV and all, right? See, some refrigerators and all, that's a common load that's always connected with the electrical sources. That depends on the temperature, inside temperature of the refrigerator, that is going to automatically switch on and switch off, right? So there may be a possibility to determine what time the particular refrigerator is going to be switched on and all. But we are not going to predict at what time we are going to switch on the TV or fans and all, right? See, this is for small houses. Just you have to think over the entire region or entire southern grid of electrical power systems. We are not going to predict very accurately what is the power consumptions of the cases, right? See, sometimes the sudden load is going to be switched on, sometimes the sudden load has to be switched off, right? See, in that situation, we are obtaining the fluctuations in the power consumption, right? See, power consumption is constant for over a period of 2 hours or 3 hours, means there won't be any power quality problems, but it may be a fluctuations. Because of these fluctuations, power quality problems are going to be existed, and installation of power electronic devices is also the major causes for producing the power quality, right? See, we are running in automatic world. Everything so are going to be automated. Everything we have to be what is this controlled with the help of power electronic devices, right? See, with the help of the power electronic devices, what is this? We are applying the firing angle to the thyristors, and with the help of them, we are switch on the particular load, switch on the electrical motor, and we are going to design what's the speed of the particular motor and all, right? See, with the help of firing signals which is applied to the voltages, what is this? The voltage waveform is going to be modified, right? See, if the voltage waveform is going to be modified with the help of pulse width modulation, again, it leads to the power quality problems like harmonics, right? See, when we have to calculate the resultant voltages, and what about the purity of the waveforms, we obtain the problems, power quality problems. So, if that installation of power electronic devices is also the causes for producing the power quality. And lightning happen in the transmission line, even in tall building. Again, there will be a voltage deviations. Very enormous amount of voltage spikes are going to be produced for a period of very short period, like milliseconds or even sometimes microseconds and all, right? See, again, it is going to lead power quality problems, right? So many other factors, fluctuations in voltage, waveforms, and change in frequency is introduced in the power line causes the power quality. So what I believe that power quality means any problem, any power problem manifested in voltage, current, or frequency deviations that results in failure or misoperation of customer equipment, right? Then causes of power quality are aging of electrical equipment, improper maintenance, fluctuations in power consumption, installation of power electronic devices, lightning, and many other factors like fluctuations in voltage waveforms and change in frequency introduced in the power line causes the power quality, right? And power quality disturbances. Actually, after the IEC standard, the power quality disturbances are majorly classified into the following three categories: interruption, sag, and swell. Interruption, sag, and swell. What is interruption? Interruption means any the voltage magnitude is changes less than zero point 0.1 per unit. Right? I hope you understand well what is per unit. What are the reason we go for a per unit concept and all in power system network? We power system analysis and stability subject. We studied the concept of a per unit. Right? So any voltage deviation less than zero point 0.1 per unit, that problem, that power quality problem is called as interruption, right? Then sag, sag, the voltage magnitude is varied 0.1 per unit to 0.9 per unit. Any voltage deviated 0.1 per unit to 0.9 per unit. The disturbances are called as sag, and swell it is defined like this: any voltage deviation 1.1 to 1.8 per unit, right? So if voltage reduces means sag, voltage increases means swell, and very small amount of voltage variation is called as interruption, right? So this is the three major categories of power quality problems: interruption, sag, and swell, right? These are classified based on the voltage magnitude deviations, right? Then again, the power quality problems are classified based on the time duration. How long the particular fault is going to exist in the power system network, right? Uh, um, it is called as the instantaneous, momentary, and the temporary, right? For instantaneous power quality problem, the power quality problem existed in 0.5 to 30 number of fast cycles, right? See, we know the 50 hertz frequency is rated frequency we are using in Indian standard. In that 50 hertz, we know all well 50 number of completed cycles per second. Right? In that 50 number of completed cycles per second, 0.5 to 30 number of cycles, the problem is existed. 0.5 to 30 number of cycles, the problem is existed. The problem, it may be a interruption, sag or spell, whatever may be that. Right? Under this category, the power quality problem is instantaneous. The power quality problem is instantaneous. So for instantaneous interruption, power quality problem existed from 0.5 to 30 number of cycles, and we know well for interruption less than 0.1 per unit voltage is going to be deviated. All right. Then instantaneous sag, again the time duration is 0.5 to 30 number of cycles. Then for momentary cases, the duration is the increases from the instantaneous, right? From the name itself, we understand well the instantaneous, momentary, and temporary, right? See, for momentary, 30 number of cycles to 3 seconds, right? 3 seconds means how long? 150 cycles. 30 cycles to 150 cycles. The problem is existing in the power system network. The problem is under the category of momentary. Again, it has the three classifications: momentary interruption, momentary sag, and momentary swell. Again, the interruption is less than 0.1 per unit. Sag means 0.1 per unit to 0.9 per unit, and for swell 1.1 per unit to 1.4 per unit. And for temporary interruption, the problem existing from 3 seconds to 1 minute time duration. 3 seconds to 1 minute time duration. The problems are classified as temporary, right? So as per IEC standard, the power quality problems are classified mainly the following categories: instantaneous interruption, instantaneous sag swell, and momentary interruption sag swell, and temporary interruption sag swell, and finally harmonic. And for harmonics, duration is steady state, right? So for the whole entire part, we obtain the harmonics, and the voltage deviation is 0 to 20 percentage, right? So this is the power quality disturbance category based on the IEC standard, right? When we look at what are the impacts of a power quality problems, that improper overheating of equipment. Once the power quality problem existing in the transmission line, or it could be existing in the electrical devices, that electrical devices get overheated. We know well energy neither created nor destroyed, right? The one form of energy is going to convert it into another form of energy. So in that situation, if electrical devices are getting overheated, what is this? Some energy is going to be wasted out, right? Instead of converting like electrical into mechanical, or electrical into whatever may be that heat energy or thermal energy. What is this? Here, some heat is going to be produced, means unnecessarily some energy is going to be wasted out, right? So some energy is wasted. That's why overheat is produced on the electrical equipment, right? So improper overheating of equipment. Right? See, each and every electrical devices produces some of the losses, right? So already it produces losses. So because of these losses, some heat is going to existing, right? In order to overcome the problem, each and every electrical devices are going to cool with there are some cooling systems, right? But in the presence of power quality, what is this? Improper overheating is going to be existed in the electrical equipment. So what is this? We are not going to concentrate about the overheating of the particular equipment. That particular equipment, it will be insulator or bushing or whatever maybe that, like electronic power electronic devices or motors. It may be burst out. Sometimes it may be burst out, right? Then damage of home electronic appliances. It's also be the impact of the power quality problems. And the tripping drive system at automated manufacturing process, right? For automated manufacturing process and all, unnecessarily the particular devices is going to be trip out, right? It's not going to be automated, right? Then misoperation of protective relays. Instead of switch on the circuit breaker, it may be switched off, right? instead of switch off, it may be a switch on, right? This is the misoperation of a protective relays, because the relays are going to be sensed what's the voltage that has to be processed over the particular places. It may be a transmission line, or it may be any electrical equipment which is going to be protected with the help of relays and circuit breaker concept, right? See, in that situation, if heavy voltages is going to be transmitted for a period of some 3 minutes and all, what is this? It is going to be operated, right? But the power quality problems will not going to be exist for longer duration. But instead, what is this? The protective relays are going to be missed operations and all, right? See, these are all the impacts of the power quality problem. Then malfunction of computers and communication equipment also be there, and increasing the power demand. Right? See, just now I explained to you that because of the power quality, some overheat is going to be produced. So that overheat is going to increase the power demand, because we know well energy neither created and not destroyed. Right? See, one form of energy is going to be converted into another form of energy. So some heat is produced means unnecessarily we are utilizing the energy. We are wasting the energy in the form of heat. So automatically it increases the power demand, right? So these are all the impacts of the power quality. And when we look at what are the benefits to the society, uh, energy and electricity bill are going to be saved. Once if we had to concentrate what is the power quality, and we had to arrange some suitable remedial actions to the power quality problem, energy and electricity bills are going to be saved up, and improved equipment, electronic and lighting performances, protection and longevity, right? Everything are going to be improved, and the duration of working period is going to be increased with the help of a power quality solution, right? Then reduce the downtime, maintenance and replacement costs of a generator, right? See, we are not going to suddenly switch on the generator, electrical generator, or suddenly switch off the electrical generator, right? The for particular operation, it requires some certain period of time to switch on the generators and switch off the generator. So whenever we have to maintain the power quality, what is this? These problems and all not going to be existed, right? And voltage improvement and phase balancing, we are going to maintain the same voltages, same 120-degree phase displacement in between all the three phases. And the power factor is also going to be very good when we have to do the power quality mitigation methods, right? Then reactive power, apparent power, everything are going to be good, and real power demand is going to be happen when we have to do the remedial actions on the power quality problems in the power system area, right? Then power quality applications, where are the places where the power quality needed? It needed in any data center, right? The data center means that should require a proper voltages, frequency levels and all, right? That's why in most of the places they are using the UPS, right? That will minimizing the loss of data, right? If there is any power quality problem occur in the data center, there may be a lot of chances for losing the data. So the data center need a power quality uh, cases. Then medical equipment is minimizing the noise by stabilized power, and hospital is required broadcasting. Industrial like stabilized production of commodities by minimizing the variation, the quality of products produced and all. They need a power quality, right? Okay. Then objective not that problem statement. All right. Okay. Existing. See, when we look at what are the existing method available to determine the power quality problems: Fourier transform, fast Fourier transform, short time Fourier transform, S transform, wavelet transform, Hilbert transform, and fuzzy logic and artificial neural network. These are all the existing method available to determine the power quality problems. Right now, I will explain to you that how the data are going to be used, how the data are going to be analyzed in order to do the power quality problem, right? When we look at the summary of literature review, that Fourier transform of a signal does not contain local information, right? The Fourier transform FT of a signal does not contain local information, that it consumes more time for converting time domain into frequency domain. It consumes more time to convert a time domain into frequency domain. Normally, why we go for Fourier transform, we have to take out the frequency point of time. At particular instant, what is the frequency? This is what we are going to extract it from the Fourier transform. So whenever we go to that Fourier transform, that local information is not going to be contained, and it consumes more time for converting, right? And then in fast Fourier transform, the waveforms have been analyzed digitally, and the waveforms can be captured in a relatively short time. In fast Fourier transform, the waveforms have been analyzed digitally, and the waveform can be captured in a relatively short time. This short uh, capture time can have many advantages, right? Then fast Fourier transform cannot identify spikes in signals as cosine and sine alone are used, and due to nature of the nonlinear or quality disturbances, discrete Fourier transform and the fast Fourier transform are not effective in detecting the disturbances waveforms. Right? See, we are not going to assume that power quality, the power system parameters like voltage and current are pure sinusoidal and cosine waveforms. Right? They have many disturbances over that. So DFT and FFT are not effective in detecting the disturbance waveforms, right? Then preset resolution problems have occurred in a short time Fourier transform while using the variable length window. It is overcome by wavelet transform. Actually, the short time Fourier transform have a preset resolution problem. It is going to be overcome by wavelet transform. Here in wavelet transform, window size varies, and it can identify spikes in signals and all. Wavelet transform has locally time frequency analysis, and short signal pieces also have significance, right? Then in HT, Hilbert transform, it can generate analytical signal, and it provides the information about the amplitude and the phase of the signal. And the Hilbert Quang transform provides the information about the instantaneous amplitude and the instantaneous frequencies for each signal frequencies present at a different instances, right? Then in conclusion, many methods available to classify the power quality events, such as the Fourier transform, FFT, short time Fourier transform, wavelet packet transform, Hilbert transform, and a Hilbert Quang transform. And combination of these transformations with intelligent techniques such as fuzzy logic and neural network. Each of them has their own limitation, such as inability to determine the power quality at which the signal is non-stationary. Right? The signal is non-stationary, and accuracy of determinations that we know well. Signals which are in our system is not going to be the stationary, right? For this work, I have collected the data from KSR textile mills. Electrical disturbance database have been collected using three-phase power quality analyzer at the KSR textile mills, where different capacity from the concerned working places collected the data from the knowledge of a database. 3,500 plus one signal. That one signal is the reference signal have been generated using MATLAB simulation for future analysis. Right. This is the sample waveform at the KSR textile mills for 40 minutes duration. Right. Hope my screen is visible to all. Right. Am I correct? Is it visible? Is it enlarged? Yes or no? Any one of them? Am I audible? Hello?
Yes, sir. Yes,
Yeah,
sir.
yeah. See, this is for 40 minutes time duration of power quality analyzer. See, it has the three phase voltages like red, yellow, and blue, right? Normally, the curve was starting from right to left, right? See here, the curve is starting, right? Then it will go, right? So, for a 40 minutes duration, I have captured the waveforms, right? Then the figure 2 shows the peak voltage in volts, versus time in minutes. Where are the places that obtain the peak voltages, right? So the peak voltages is 350 voltages and all they obtained, right? So this is the figure 1 and 2. And then when we look at the active power in kilowatts versus time in minutes, again it's the 40 minutes duration of time period. For this, it obtained 61.12 kilowatts for R phase, and for yellow phase it's not visible, and for B phase 56.14 kilowatts of its uptime, right? So for a 40 minutes duration, I have collected all the data, right? What is the voltages, what is the peak voltage, what is the active power in kilowatts versus time, and what is the apparent power in kVA versus the time in minutes. Then what about the reactive power, kVAR? The same cases, what is the reactive power, and what about the unbalanced voltages, right? Unbalanced voltages for this cancer textile mills, that unbalanced voltage is not going to be much, right? It will be about only 2 to 10 voltage is the unbalanced voltage. And and this is the instantaneous voltages involved for all the three phases are neutral for two complete cycles, right? See, this is for 40 minutes duration. This is 40 minutes duration. What about the waveforms? Everything are observed. In addition with that, from the database, I have collected the data for two complete cycles. We know well per second 50 number of completed cycles. Just you have to imagine that per second 50 number of completed cycles, and how long it would be for 1 minute duration and 40 minutes duration, right? So from the 40 minutes entire duration of a time period, I have calculated, I have observed the database, I have created the database for two complete cycles. For these two complete cycles, I retrieve the data from the cases that, so for these two completed cycles, the voltage is called as instantaneous voltage. Instantaneous voltage involves for all the three phases are neutral for two complete cycles, right? See, for this case, I obtained 237.1 volt in the red, and for blue phase, B phase 235.1 volt. Then in figure 8, it shows the instantaneous current in amperes for all the three phases are neutral for again two completed cycles, right? See, for these two completed cycles, what is the current for red phase? It's around 274 ampere, right? 274 ampere, and blue and yellow line 247, and the blue the B phases 260 ampere. Then for neutral alone, it carries 29 ampere. Neutral alone, it carries the 29 ampere. But when we go to our domestic appliances, in-house appliances and all, maximum 32 ampere only going to flow, right? See, actually in case of textile mill, 6 number of units are there. Actually at the time of measuring the power quality with the help of power quality analyzer, only 4 units are running, right? So under these 4 units, it consumes 274 ampere. Just you have to imagine all the 6 number of units are running. What about the current rating, current that has taken from the bus bar, right? So this is the instantaneous current in amps for all the three phases are neutral for two completed cycles. Then in addition with the large amount of data, I have considered small amount of data to test system for identifying power quality in small loads, right? See how that power quality analyzer is going to be measured. Just it is going to be connected across the load. I have to measure the power quality, and for these cases, I have taken electronic ballast, right? See, for this electronic ballast and all, it won't take more than five, more than plus or minus 5 volts and all, right? For this electronic ballast, I have captured the screenshot for instantaneous voltage in volts versus time, and a screenshot for instantaneous current in ampere versus time. Similarly, I have taken the captured the data from central processing unit and monitor, DS2, fan, electrical fan I have used, right? In addition with that, I have collected the data from data for harmonics too. Voltage harmonic data from small electrical load. Actually, I have considered 15th number of harmonics for all the cases, right? For the cases, CPU, monitor, BSO, fan, electronic balance, everything are have considered that, and I have observed the database, right? From this database only, I had to done the power quality analysis. That's why uh, the topic is data analytics in power quality disturbance analysis, right? See, these are all the harmonic data collection from the reference papers for the same cases, right? Electronic balance, TSO, fans, and all, right? Here, here I had to generate the generation of electrical disturbance data to meet out the first objective. Actually, my first objective is to generate the real-time database for power quality disturbances. Generate the real-time database for power quality disturbances. Right. See, from this 40 minutes duration of time period, I have collected the data, and from this real-time data, I am segregating the electrical disturbances, right? See, this is the waveforms for instantaneous interruptions. We know well for instantaneous means the time duration is, what is this, 0.5 to 30 number of cycles. The time duration is 0.5 to 30 number of cycles. The variation is going to be occurred, and the voltage variation is less than 0.1 per unit, right? See, for this case, the voltage variation, the blue color line waveforms shows 0.092 voltage variation, and green line shows 0.078 variation, and again red for the various 1, 2, 3, 4, 5. 5 waveforms have been shown for different waveforms for under the category of instantaneous interruption, right? See, this is the first objective. Similarly, I have created the database for all the 7 number of disturbances. Actually, in data analytics, if I given the data in a tabulated manner, it's very difficult to understand how it is generated and all, right? See, that's why I have created the waveform with the help of a database, right? See, this is the waveforms for sample signals for instantaneous sag, right? For in order to understand the waveforms, I have given only 5 number of signals, but actually I have created 500 number of signals for each and every disturbances, right? See, this is the sample signals for instantaneous sag. For sag means we know well 0.1 to 0.8 per unit variation, and we know well for instantaneous, again the cycle duration is 0.5 to 30 number of cycles. Alright. See, as per this IEC standard, I have created the real-time database for instantaneous sag, and similarly this is for instantaneous well, and this is the waveform for momentary interruption. When we go for momentary, the time duration is very longer, right? 30 cycles to 3 minutes they have to taken, right? See, that's why uh, waveform I have taken 1 second, right? Out of 1 second, how many cycles, how many number of cycles it has to be varied, right? So this is the waveform for momentary interruption, and this is the waveform for momentary sag. Similarly, I have created the database for momentary swell and harmonics, right? Again, the harmonics, right? So with this power quality, with this power quality analyzer, I have created a real-time database for different categories of electrical disturbances based on the IEC standards. Right now, I go to the proposed method. The proposed method is Hilbert-Hwang transformation method. In that, the empirical mode decomposition (EMD), simply we call it as the EMD, produces the mono components called the intrinsic mode function from the original signal. Right? Actually, the Hilbert transform is applied on intrinsic mode function to obtain instantaneous frequency and the instantaneous amplitude. The features obtained are mean value, standard deviation, normalization, maximum value of instantaneous frequency and the minimum value of instantaneous frequency of an intrinsic mode function, right? For each and every intrinsic mode function, I have to obtain the instantaneous frequency and instantaneous amplitude. For each instantaneous frequency, I have to create the pi number of the features. They are mean value, standard deviation, normalization, maximum and minimum. Everything are data. Everything are database, right? See, one, with the help of power quality analyzer data, I have created the real-time database for different categories of power quality problems. From this database, I have to obtain the empirical mode decomposition. Again, I am doing the data analytics, right? Empirical mode decomposition. From that empirical mode decomposition, I have to find out the instantaneous frequency and instantaneous amplitude of each and every intrinsic mode function. Again, from each of instantaneous frequency and instantaneous amplitude, I have to find out the following 5 plus 5, 10 number of features. Right. Finally, two more features are going to be calculated. That is log to energy of fine to coarse and coarse to fine. Right. Actually, TO2 has to be represented in the name numerical letter 2. Fine to coarse and coarse to fine waveforms of an intrinsic mode function. Right. See, this is what I am going to do, that data analytics. Right. I have created a database, and with the help of a database, I am doing the data analytics. From this data analytics, I am going to ensure the power system have a particular problem or not. If it is so, again we go for some remedial actions. Then only the power quality problems are going to be rectified. Okay. Now, when we look at the flowchart of empirical mode decomposition, what is this? The first, we have to load the input voltage waveform X, right? See, from the database, I have created 7 categories of power quality disturbances. For each and every disturbances, I have created 500 number of signals, right? See, we have to take the signals one by one, right? We have to load the input voltage waveform X, and it takes the residue, right? For residue, R is equal to X, and we have to determine the mean of the signal M. Mean of the signal M. How to determine that mean of signal M? Just we have to compute the envelope of maximum, right? We have to determine the envelope maximum and put it as A, and we have to compute the envelope maximum B, and from that envelope, maximum envelope and minimum envelope, we have to do the average value. M is equal to A plus B by 2, right? From that average value, what is this input voltage has to be subtracted from this average, and new average has to be taken as the M signal. M is equal to X minus M, where X is the old signal and M is the average value. Right now, here we have to determine the squared difference. What is the squared difference of this M signal? If the squared difference Ft is less than or equal to 0.2, our convergence is okay. Unless otherwise, we are going to do again and again what is the maximum envelope. We have to compute what is the minimum envelope, and from this we have to do the average, and from that average we are going to subtract it. Right? This is going to be done. Right? Once the squared difference is less than or equal to 0.2, that signal M is called as the intrinsic mode function. Right? This is big. We are going to determine the intrinsic mode function. So IMF of T is equal to M. Again, the residue is going to be calculated. R is equal to R minus M. Just how it is going to calculate the value, right? See, R is equal to R minus M, and from that value, again, we are going to determine maximum R minus minimum R is less than maximum of X minus minimum of X into 10 to the power of minus 10. Right? Up to this convergence, we are going to do repeatedly. This is the flowchart of a empirical mode decomposition process. That empirical mode decomposition process is going to be done with all kinds of disturbances. Right? We have created 7 number of disturbances, and for each disturbances 500 number of signals. right? So just you have to imagine how long the database, right? So from that cases, we are going to do the empirical mode of determination. See, just this is the flow chart, and with the help of algorithm, I will explain to you that how the Hilbert-Quang transform is going to be processed, right? See, identify all local maxima of x of t, connect the point using the cubic spline, right? Then the second step, identify all local minima of x of t, connect the points using a cubic line. We obtain the waveforms like this, right? The blue color line is the actual waveform, and the green color line is, it shows the upper envelope, right? Interpolated upper envelope, and red in color shows the interpolated lower envelope, right? This is what A and B, right? And black in color is interpolated average values, right? See, M is equal to A plus B by 2. This is what we are going to do for each and every database. We see lower envelope, upper envelope, and mean of the envelopes along with the signals. See, the average is computed as by the formula M is equal to A plus B by 2, where A is the upper envelope, B is the lower envelope, right? And extract the details from the signal called the new signal as shown in figure 29 using the following equation, Hilbert transform. H1 of t is equal to h of t minus m1, right? Where m1 is going to be determined from the equation number 1, right? Now again we are going to take it that h1 of t is the new signal to this. To determine if h1 of t is the intrinsic mode function using equation p, again we got a signals like this, right? See, the red in color shows the old signal, and blue line shows the new signals, right? See, this is the waveform. It gives the relations in between voltage and time period, right? See, for 0.5 seconds, how the variations are going to be happen, right? Then for normalize the squared difference SD, we are going to calculate with the help of the formula number 3, right? From that, we are going to determine whether the squared difference is less than or equal to 0.2. In order to find the additional intrinsic mode functions, H11 of t is taken as the new signal after the kth iteration. So H1 k of t is equal to H1 of k minus 1 of t minus m1 of k. And from this, the step 6 is repeated. Sorry, frequently I received the enormous amount of messages. Very sorry to say. The step 6 is repeated until all the intrinsic mode functions and the residue are obtained. Equation 5 has been used to check this condition. Maximum of R minus minimum of R less than maximum of X minus minimum of X into 10 to the power of minus 10. Right? See, up to this, we are going to determine the intrinsic mode functions. Right? See that the formula, the equation 5 is satisfied until we are going to determine. Right? That will show the number of intrinsic mode functions. Right? Then C2F, cost to find, is calculated as the cost to find 1 is equal to IMF of k. Then C2F2 is equal to previous, that is the old, current intrinsic mode function plus old intrinsic mode function, IMF k plus IMF of k minus 1. Similarly, we are going to calculate for all the cost to find value for all the intrinsic mode functions up to k. That is kth iteration. C2 f of k is equal to intrinsic mode functions IMF of k plus IMF of k minus 1 plus IMF of k minus 2 up to IMF 1, where IMF k is the final intrinsic mode functions obtained. This is the waveform. It shows how course to find waveforms is going to be getting from the instantaneous tag signals, right? Similarly, we are going to determine for all the 7 number of signals. For each and every signals, I have created 500 number of database, right? Then find the course function, just the ulta of the previous case. F2C1 is equal to IMF1, F2C2 is equal to IMF1 plus IMF2, and F2CK is equal to IMF1 plus IMF2 plus IMFK, right? From end to origin, we are moving, and find two courses from origin to end, we are moving, right? This is the difference in between course to find and find to course, right? Then Hilbert transform is applied for each intrinsic mode function, and analytical signal is obtained as x h of t using the formula 12. This is the basic formula to determine the Hilbert transform, right? From this analytical signal can be calculated using the formula x analytical of t is equal to intrinsic mode function IMF of t plus imagination of x h of t, where instantaneous phase of IMF t is calculated by the formula equation number 14. Theta of t is equal to tan inverse of x h of t by intrinsic mode function of time t, right? Then from this I had to determine the instantaneous frequency IF, where IF are obtained from the analytical signal as the IF is equal to 0.5 into angle of minus x analytical t plus 1 into conjugation of x analytical t minus 1 of plus pi by 2 into pi. From that equation number 15, we can calculate the intrinsic mode instantaneous frequency for all the intrinsic mode functions, right? For this database, I have created up to 5 number of instantaneous frequencies. IF 5, IF 1, 2, 3, 4, up to 5, right? Similarly, I have to determine the instantaneous amplitude. IA are obtained from the analytical signal as the IA is equal to square root of IMF of t square plus imagination of x h of t whole square, right? Similarly, for this case again, I had to determine for all the intrinsic mode functions like IA1 to IA5, right? Then I had to determine the features, right? What are the features? Features are mean, standard deviation, normalization, maximum and minimum, right? See, this is what we are doing the data analytics, right? Database management system. How the particular data is going to be used and what are the features that we have to determine from the set of databases, right? See, we know well instantaneous frequencies mean value that is equal to summation of IF of I by total number of samples, right? N SFR, that is the total number of samples in a frame. Number of samples in a frame. From the equation number 17, we can determine the mean value. This is the as usual formula. We are all know how to determine the mean value. Then for standard deviation, summation of IF of I minus IF mean divided by number of samples, we obtain what is the standard deviation from one another. Then normalization of IF squared, we obtain the normalization functions, right? And similarly, find the features mean, standard deviation, normalization, maximum and minimum of IA, right? Then how to determine maximum and minimum of IF? We have a set of database. From that database, we have to identify which particular data is the maximum value and which one has the minimum value, right? Again, data analytics, right? So these mean, standard deviation, normalization has to be determined with the help of formula, and the maximum and the minimum value has to be obtained by comparing the data, right? So totally 5 number of features has to be determined, from instantaneous frequency, and another 5 number of features has to be determined from instantaneous amplitude. So totally 10. In addition, course to find to course. So totally 12 number of features are going to be obtained, right? See, this is the features value: IF mean, IF standard deviation, IF normalization, IF maximum and IF minimum, and IA minimum, IA standard deviation, IA normalization, and shown. Finally, find to course and course to find for all the intrinsic mode functions: IMF1, IMF2, IMF3, IMF4, and IMF5. This is the database for single waveform, right? Single waveform as per this 500 number of signals under the disturbance category, and again the disturbances are 7, right? So now you have to imagine how long the database is, right? What is the strength of this database? Okay. Then electrical disturbance category, I have taken for this analysis only 7. They are instantaneous interruption, instantaneous sag, instantaneous swell, momentary interruption, momentary sag, and the momentary swell. Finally, harmonic. And I have created the label name as disturbance 1, 2, 3 up to disturbances are 7. Right? And when we look at the minimum mean value of instantaneous frequency, it's shown in the figure. Right? See, this is the mean value of instantaneous frequency. Right? Now the disturbance signals are disturbance signal 1, disturbance signal 1. What is the disturbance signal 1? That is the instantaneous sag, right? Sorry, instantaneous interruption. For this instantaneous interruption, 500 number of signals are there. For all the 500 number of signals, mean value of IF is shown in this plot, shown in this diagram, right? See, this is very, very difficulty to give a database for mean value of IF for all the 500 number of signals, right? See, that's why I have created a waveform and it shows. So it's very easily to understand how the mean value of IF is existed in existed for all 500 number of disturbances, right? Similarly, mean value of instantaneous amplitude for the same disturbances, for the same disturbance signal 1, right? And this is the what is this standard deviation of instantaneous frequency and the standard deviation of instantaneous amplitude, right? So this is the disturbance 1 feature. Disturbance 1 is the instantaneous interruption. The features are mean value of IF, mean value of IA, standard deviation of IF, and standard deviation of IA. So for those 4 number of features for all the 500 number of signals I have created with the database, right? Similarly, this is the features: normalization of instantaneous frequency, normalization of instantaneous amplitude, and energy of time to course and course to time. Again, the remaining 4 features are going to be shown for the disturbance signal 1. As per that, I told you that 7 number of disturbance signals I have created from the database, right? And this is the another 4 category: maximum of instantaneous frequency, minimum of instantaneous frequency, maximum of instantaneous amplitude, and minimum of instantaneous amplitude for disturbance 1. So for all the 12 number of features, I have calculated under the category of disturbance 1. Disturbance 1 is instantaneous interruption, right? Similarly, second disturbances, disturbance 2, the same 4 features, then again 4 features, and again 4 more features: maximum of instantaneous frequency, minimum of instantaneous frequency, maximum of IA, and minimum of IA. Similarly, I had to derive the database for all the disturbances: disturbance 3, disturbance 3 again, disturbance 4, disturbance 4, 5, 5. These are all the various data, right? See, in this very difficulty to show again and again, I'm showing that, I'm explaining that it is very difficulty to showcase the database, right? Instead of showing in tabulated form, if I had to show it in a graphical form, it's very easy to understand how the data are going to be varied, right? So this is that I had to create a database for all the 7 number of disturbances, right? Here the summary of features. A concept of envelope identifying and envelope subtraction has been proposed by Kwong under the name of empirical mode decomposition. The statistical method are used to extract representative features from instantaneous amplitude and instantaneous frequency. For each of electrical disturbances, totally 72,000 features have been generated. So totally how many features are generated? 72,000. A total of 5,04,000 features have been generated for 7 number of electrical disturbances. For each and every electrical disturbances, I have created a 500 number of signals. Right? This is my work. Right? See, you had to create a more than 500 number of signals too. Again, the database is going to be enlarged. Again, the accuracy of our results is very, 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 very accurate one, right? So for these cases, 72,000 features have been generated from the database, and 504,000 features have been generated for 7 numbers of electrical disturbances. These feature values are used to train the artificial neural networks, right? Now, the artificial neural network is the backpropagation algorithm from the Hilbert-Quang transformation. I have created 12 number of features. With these 12 number of features, I'm going to train the backpropagation algorithm and testing the backpropagation algorithm for power quality disturbance classification. Right? Steps involved in forward propagation. This is a very generalized algorithm. This is available in even in Google too. You may Google it and you may find out what is the um, what is the algorithm for the backpropagation algorithm, right? See, the weights of network are initialized. The inputs and outputs pattern are presented to the network. The output of each node in the successive layer is calculated. The following formula: output of a node is equal to 1 plus exponential minus wij. W is the weight, wij into xi. The error of a pattern is calculated. E of t is equal to 1 by 2 summation of d by p minus ot whole square, right? See, then reverse propagation. The error for the nodes in the output layer is calculated. The formula 24. The weights between the output layer and the hidden layers are updated to the equation number 25. The error for the nodes in the hidden layer is calculated with the help of equation number 26. These are all the generalized equation. This is available in every textbook or even in Google too. You may Google it, right? With the help of backpropagation algorithm, we can train the systems. When all the training patterns are presented, a cycle of iteration or epoch is completed. The errors of all the training patterns are calculated and displayed and monitored as the mean square error MSE, right? Then the corresponding flowchart shown in the next slide, how the backpropagation algorithm is functioning, right? When we look at the results of Hilbert-Quang transformation with backpropagation algorithm, it shows like this, right? See, the result shows the signal patterns versus average of feature values. Average of feature value versus signal patterns they have calculated. For 500 number of signal patterns, it's classified identification of instantaneous interruption by HTTP. Instantaneous interruption, this is the disturbance signal 1. I have calculated. This is where the Hilbert-Quang transformation and the backpropagation algorithms are functioning, right? It's almost classified, right? And similarly, when we look at instantaneous tag, how the HTTP is performing, it shows in the figure number 53. Similarly, it shows the results for all the 7 number of disturbances. Identification of instantaneous swell, identification of momentary interruption, identification of momentary sag, and identification of momentary swell, finally harmonic, right? So this is the first cases, right? How the Hilbert-Quang transformation methods are used and how it is going to use to train and testing the backpropagation algorithm, right? Then HST RBF apply the radial basis function. Again, the steps are very generalized one. It's available in even Google too. Number of input is equal to 12 because we use the 12 number of features. Those 12 number of features are mean value, normalization, standard deviation, maximum and the minimum, find to coarse and coarse to fine. Similarly, for it is instantaneous frequency and instantaneous amplitude. We totally obtain 12 number of inputs and the number of patterns is equal to 500 because I have used the 500 number of signals for this. So number of centers is equal to 500 and it calculate our radial basis function as RBF equal to exponential of minus x. Calculate The matrix G is equal to RBF, A is equal to G transpose into G, and again calculate B is equal to A inverse and calculate the error E is equal to B into GT, and calculate the final weight F is equal to E into D, and store the final weights in a file. Right? This is what the radial basis function is going to use to train the system, and the flowchart, corresponding flowchart shown in this figure. And when we look at the results of HSD RBF for various signals, it's available from the figure number 60 to 66, right? The figure number 60 shows identification of instantaneous interruption by HSD RBF, identification of instantaneous tag by HSD RBF, and third disturbance, instantaneous swell, and momentary interruption, momentary sag, and momentary swell, and finally harmonic by HSD RBF. Right? Then the third category, Hilbert-Huang transformation with a locally weighted projection regression method, LWPR. Right? See, in that the algorithm steps are input to LWPR. As usual, right? What input we are going to train the system for backpropagation algorithm, radial basis function. The same algorithm is going to use for LWPR to input to LWPR is equal to extracted features from HST. Initialize the LWPR using diagonal distances matrix alpha, normalization, meta rate, and initial lambda. Many other variables can be initialized or more are made up constants depending upon the requirement. Create random numbers. Choose input and target output of a pattern. Find global mean and variance of the pattern. Normalize the input and output. Compute the weight, and check if new random field has to be added. Right? Find mean squared error between the targets and the estimated values, and repeat the steps 5 to 9 until all the patterns are presented. Right? See, this is the algorithm part, locally weighted projection regression method, and the flowchart, corresponding flowchart is shown in the forthcoming slides. Right? Then when we look at the results of HST LWPR, it shows for all the 7 number of disturbance categories: instantaneous interruption, instantaneous sag, instantaneous swell, momentary interruption, momentary sag, and momentary swell, finally harmonic. Right? This is the in order to meet out the second objective, what is this? Developing new combination of algorithms that will extract characteristics of electrical disturbance signals. The algorithms are Hilbert-Huang transform and artificial neural networks. To meet out the third objective, compare the proposed algorithm with the existing algorithm. Existing algorithm is the HT RBF. Features are extracted by Hilbert transform and trained and tested with the radial basis function. And finally, I had to compare with all the 5 number of categories. Right? HT, HT RBF, HST RBF, HST BPA, HST LWPR, right? And actual cases. I have compared all the cases, and the comparison results are shown in this figure. How the particular data is going to be, particular method is going to be effective, right? Then comparison of algorithms by training time period. Actually, for instantaneous interruption, HST BPA, it shows the various time period. HST BPA, RBF, HST LWPR, and HT RBA. Right? Normally, that HST LWPR, they had to use many variances. In many places, we had to do that update the systems. That's why it takes longer time period for all the categories. Almost all the 7 number of categories. HSD LWPR takes longer time period because of a lengthy algorithm, right? It has many number of variables. Each and everything are going to be updated in a frequent manner, right? That's why it takes a longer time period. But in the case of HSD BPA, HSD RBF, and HT RBF and all, very less time they had to do it. Only the reason is they have a very nominal. They have only nominal references. They are not going to update in nook and corner of that, right? That's why the training time duration of HSD LWPR takes longer time period than others, right? Then comparison of algorithm by percentage of classification instantaneous interruption and instantaneous lag. It shows like this from frame by frame. It shows for all the categories. Frame 1 to frame 12 for all the category HST BPA, HSD RBF, HSD LWPR, and HSD RBF. This is for instantaneous interruption, and the second column shows the instantaneous lag. Similarly, for the tabulation for all the 7 number of categories: instantaneous swell, momentary interruption, momentary swell, momentary sag, and momentary swell, and finally harmonic. Right. Then analysis of Hilbert-Wong transform. Depending on the number of frequencies present in an electrical fault signal, equal number of mono components are obtained. Only when the magnitude of harmonics above a threshold of 2 volts, the corresponding mono component is developed. Based on the number of samples considered in a frame, the accuracy of the feature value varies. A minimum of 5 cycles in each fault is considered, and hence one frame consists of 256 samples per cycle. The presence of noise in the signal is not treated as harmonic, and the noise is identified from the log 2 of fine to coarse and the coarse to fine waveforms. Hence, first few intrinsic mode functions alone are considered for finding out the instantaneous frequency and the instantaneous amplitude. An analysis of HSD combined with the BPA less than 4 seconds has been consumed during the training of BPA network, which is better than 30 seconds of LWPR network. Just now I told you that why LWPR takes longer time for the training. HSD combined with the BPA for classifying the PQ problem shows the fairly acceptable results with an error tolerance of 0.05 for real-time electrical disturbance. Analysis of HSD combined with LWPR, duration of training time is more than 30 seconds. It is fairly unacceptable compared to BPA and RBF network training duration. The LWPR network gives good response for the electrical disturbances such as harmonic, momentary interruption, momentary sag, and the momentary swell than BPA network. On an average, it classifies the electrical disturbances with an error tolerance of 0.09. Analysis of HSD combined with RBF less than 2 seconds. It has been consumed for training the radial basis function network, which is the best one than BPA and LWPR network. This approach gives the best results with an error tolerance of 0.0002 compared to the error tolerance of 0.09 in LWPR and 0.05 in backpropagation algorithm. To meet out the fourth objective, validating the algorithm with the measured data. The effectiveness of the proposed algorithm has been tested by comparing with the measured data from power quality analyzer meter at various conditions such as fully loaded, all the units are running condition, partially loaded, and small electrical appliances of textile mills. Then validation of HSD BPA, HSD RBF, HSD LWPR are given in the table. And finally, conclusion: because of the presence of much updation in LWPR and receptive field parameters, time consumption at LWPR network is much higher than the RBF network. Compared to BPA, RBF, training time is very low because the BPA network consumes time to reduce the MSE, right? The RBF and LWPR network have used 1 to 20 number of iterations during the training period, whereas BPA used up to 400 iterations. 12 number of features have been used to train the HSD RBF method, whereas HSD RBF used only 4 features. Thus, the HSD RBF consumes little more time to train the network than HSD RBF. Instantaneous electrical disturbances have been classified poorly by HSD LWPR network than HSD BPA network. Momentary electrical disturbances have been classified poorly by HSD BPA and network than HSD LWPR network. Harmonics have been classified more accurately by all the 3 algorithms compared to HSD BPA, HSD LWPR, and HSD RBF network. HSD RBF classifies electrical disturbances very accurately, and it consumes very low time during the training period of time. The number of successive frames, voltage, and frequencies occur with a similar value helps in identifying faults with a more than 10 cycles. If the fault has the 11 to 15 cycles, then the first 5 cycles will be designed the fault category. Conclusion: the predicted results were found to be very closer to the actual target value in HST combined with RBF approach. Compared with other two techniques, hence all of the three number of analytical spread HST with RBF method is found to be the better method than other two methods for classifying the power quality disturbances because of its improved performance characteristics with regard to converging speed, oscillation in error characteristics, and accuracy of predicted value with respect to the actual values. And the limitations: HST BPA slow convergence need of spread difference in BPA and hence slow learning. Sometimes the convergence will oscillate in the local minima and will give never reach the global minima. HSD RBF work well when number of centers is less. The same case, the number of centers is more, is not going to be much suitable for the cases. HSD LWPR conditionally the algorithm is suitable only when the number of patterns are more. Okay. Then for scope for future work, again we had to create a, instead of 500 number of signals, we can create more number of signals for each category. In addition with that, again we had to consider more number of power quality problems. Then we can use the same categories. We can have a database, right? These are all the references. Thank you. Now I request the participants, if you have any doubt on my session, kindly ask me. Yeah, I will ready to share the knowledge. Hello? Hello, I am audible. Hello? Team member?
Hello, sir?
Yeah, yes, I
sure.
have completed my part.
Yes, sir. I'll ask the participants, sir, to raise their query. Participants, if you have any queries, kindly unmute your audio and then clarify your doubts. Participants, if you have any queries, unmute your audio. Otherwise, you put your doubt in the type your doubt in the chat box also. I think the session is self-explanatory, sir. It's fantastic. Thank you very much for the excellent knowledge transfer, sir. From the audience side and participant side, I think there is no doubts. Thank you very much for accepting our invitation, sir. Thank you so much, sir.
Yeah, thank you, team members of St. Joseph Engineering College. Again, thank you so much for inviting me to handle the session. Thank you. Thanks a lot.
Okay, thank you, sir.